All right, getting started today, we are finishing up week 5, and we are going to do respiratory system and gas exchange. Fairly short PowerPoint that we're going to go over today. Main points that we're going to talk about is respiration as a whole. So by definition, respiration is subdivided into 3 parts, but it's the total process of exchanging gases between the atmosphere and the body cells, so the cells can use it for some type of metabolic process. And then, of course, from that point, we have to get the gas back out again because it'll change during that time. And we use O2 as our main way of releasing energy from some of our macro molecules. So we use it for combustion reactions, and some animals they don't need to do that. Well, I shouldn't say animals, but some living things don't need to do that. Some living things might use CO2. And CO2 in combination with, like, say, the sun, for example, using the sun as energy, they can store sugar as a byproduct. And so that's what plants do, and certain algae and things like that. And then when we go and consume those substances, they've trapped some of that sun energy into the plants. And then when we consume the plants, or the animals that consume the plants, we can now release that energy that they stored using CO2 and the sun and water by using the opposite gas, carbon dioxide, or sorry, using oxygen. And then we release the carbon dioxide that the plants use, and it all ends up being one big cycle. So, photosynthesis and respiratory processes go hand in hand with each other. So we'll talk about the big idea from, our perspective, our cells, what our cells need for energy, and then where the gas exchange is actually taking place. But overall, it's a pretty short chapter. Other topics that we'll talk about is, what all is needed in order for this process to take place. Of course, the airway is necessary, but there's more to it than that. You also have to have pulmonary circulation. You have to have the right components of blood. And we'll actually pick more of that topic up later when we talk about the blood itself, which we're going to separate that out, talk about that in a different topic. We'll talk about respiratory volumes. When we change the way we breathe to meet metabolic demand, there's kind of like 2 different aspects we can change about breathing. We can change the rate, like how fast, and the depth, how deep we're breathing. So factors that go into that, and then different types of muscles that we used for those different rates and depths of breathing. And then we'll talk about certain types of respiratory conditions, like restrictive versus obstructive lung diseases. And we'll pick up with more diseases again in other chapters too. So we might talk about a little bit more with blood and anemia. We'll talk about different types of cancers toward the end of the semester, but that's pretty much a summary of what we're going to do today. And that finishes up our lecture 2 exam material. So last week was the start of lecture exam 2 material. We covered cardiophys. Tuesday of this week, we kind of finished the last little piece of cardiophys, and we did all the blood flow and pressure. Today, we're doing respiratory system and gas exchange. And then next week, there's no meeting on Tuesday because it's the 4th. Thursday, we'll do our Zoom Q&A session. So if you got any last minute questions about cardiophys, blood flow and pressure, respiratory system and gas exchange, then join me a week from today, and I can go over any of that with you. You can also email me at any time, and I will answer your questions directly. And then our projected due date for lecture 2 exam, July 10th. Following week, so this is next week. This right here is next week. The week after that, we're going to do one quick lesson and then take a quick quiz after that. So I'll start setting up some of the Zoom meetings. I haven't even posted them inside the document yet. I'll do that next week, but just to let you know what's coming up, we're going to have a 1-day kind of lecture over blood immunity lab dye. So different things you might find in certain tests, blood tests, for example. So there's a lot of different names for the different blood tests. Like you have things like CBCs, complete blood counts, and then you have metabolic panels. And the metabolic panels get lots of different names depending on what they cover, like how in depth are they. So we'll talk about some of that stuff, which is very useful, but that'll be separate. So initially this was intended to go with the cardio, and we're going to separate it out, take it separately. So our material ends today for lecture 2 exam, and lecture 2, similar to lecture 1, 50 questions, multiple choice. So same format, but I've already got my respiratory system and gas exchange PowerPoint open. So I'm just going to switch screens, which leads us to this, minimize that. And here's one of the first things I was talking about with you. Respiration is the entire process of exchanging gas between the atmosphere and the body cells, and it gets subdivided into 3 parts, each of which needs vital components. So the way I kind of memorize it is we have to take certain gases from the atmosphere. In our case, it's O2, right? And that needs to enter into the lungs. From the lungs, it's going to go to the blood. From the blood, it's going to go to the cells. And while we're in the cells, that O2 is going to get converted into CO2, right? And the CO2 will then leave the cells, go into the blood. From the blood, it's going to go into the lungs and then back out to the atmosphere again. So we kind of started with gas in the atmosphere. It followed this little process. We're going to exchange those gases through metabolic processes, right? Like the aerobic respiration of glucose, for example. So when we do C6H12O6 plus 6O2, right? That gives us 6 CO2 plus 6 H2O plus energy. And this is the primary means of making cellular ATP. So we get ATP plus heat as our energy source. So that gives my cells mechanical energy, plus it keeps us warm. So that's nice. So that's our basic use of O2. Of course, this isn't the only way we can make energy, but it is the primary means in which we make energy. You could also just burn fat if you wanted to. You could do things like beta oxidation, and it's similar to like how cars work. We burn gasoline, you have some type of air intake, and carburetor used to be what would mix those things together, the fuel plus the air, or other than gasoline's kind of like sugar. You could also use diesel if you wanted to, and diesel is more like fat. So our body works very similarly to how various different types of engines work, and technically it's vice versa. Obviously engines work similar to how our body does, but we got to extract the energy somehow. So how are we going to extract the energy? O2 is going to do that. So this gets called a combustion reaction. So this formula right here gets different names. You can call it the complete aerobic respiration of glucose, right? And we talk about that in a cellular respiration chapter in Anatomy 1, or you could just simply call this a combustion reaction, where you're going to take some type of organic substance, carbons and hydrogens, you mix it with O2, and you're always going to get CO2 plus H2O plus energy. All combustion reactions do that. So, but again, this is what respiration's for, right? So respiration talks about all of this. It's not just the lungs breathing, right? Respiration also talks about the blood transporting, right? If you don't have pulmonary circulation, how are we going to get that oxygen from the lungs to the blood, right? And then if you don't have proper hemoglobin, or if you don't have enough hemoglobin, how are we going to transport that oxygen in the blood to the cells, right? And then the cells themselves have to have proper components to be able to work. And the distance between, the blood vessels and the cells, and the distance between the alveoli and the blood vessels, that plays a big role on it too, because we have to be able to exchange those gases through diffusion, and diffusion doesn't like to travel over long distances, right? So we'll talk about how all this can break eventually. But when you get into the terms of respiration, which basically this whole page is talking about respiration right now, you can break it down into 3 parts. So as I'm going from like lungs to blood, that's what's called external respiration. If I'm going from blood to cells, that's called internal respiration. And when I'm in the cells, that's called cellular respiration. And then it just flips, right? So we go from lungs to blood, blood to cells, and then from cells back to the blood, from the blood back to the lungs, and then back out again. So easy peasy. But a lot of times people forget that this is a big concept, right? So when we were talking about sympathetic nervous system, so this is tying into old stuff. So when we were talking about sympathetic nervous system versus parasympathetic nervous system, sometimes I'll summarize all that. I'll say, you know, we have increased heart rate, increased heart contractility, and then I'll sometimes say we have increased respiration, you know, which does include things like bronchodilation, right? That's one of those, you know, direct effects. Is our airway will get open, and that's going to help with the external respiration because it's going to allow more air to get into the lungs, right? So that exchange takes place easier, but we're also speeding up how much blood gets to the lungs. We're going to increase pressure so we have more perfusion power and all that kind of good stuff. But at the same time, when we're increasing our breathing capacity, we're also going to release glycogen. So sometimes during sympathetic innervation, we increase, you know, our breakdown of glycogen, right? And glycogen is the sugar, right? And, you know, and so if we haven't eaten in a while, we need to tap into our stored reserves of sugar. So what if you ate not too long ago, then you'll have, you know, sugar from your diet floating around in your blood. But after we fasted for a while, then we have to tap into stored sugar. So under a sympathetic response, we're not going to take any chances. We're just going to go ahead and start burning glycogen, even if we have a meal that's been in the belly for a while and it's digesting and absorbing. We're just going to go ahead and break this down anyway, right? So you have glycogen stored in your liver, you have glycogen that's stored in skeletal muscles, and we're going to make that more available. So as more blood is pumping through the body and more oxygen is, you know, on the blood, we're going to make sure we have fuel to burn too, so we can do this. Big picture stuff. And then ventilation is what most people think respiration means to begin with, which is basically just the movement of air in and out of the lungs. But now we know better because we are super educated, and we know that respiration is a much larger process than just the movement of air in and out of the lungs. But unfortunately, you know, the words that describe ventilation sound more like respiration than they do ventilation, because we call it inspiration and expiration. So it's easy to get these words confused with each other. But respiration is a much larger term. So respiratory system, of course, when you think about the respiratory system, the main part you think about is the lungs. And we call that the tracheobronchoalveolar system. So, you know, it's not just the lungs. We have to have a patent airway to get in there. So if I'm going through some type of anaphylaxis and my airway closes up, then lungs are pretty useless at that point because I don't have a way to get in there. So maybe you'll have to trach them, or maybe you'll have to ventilate them in some way, shape, form, or fashion. Maybe the lungs themselves are too weak and they can't breathe on their own. So you have to ventilate them and add mechanical assistance. But, you know, obviously the airway is an important part of the respiratory system, but we can't forget the blood vessels as well. Because what good is it if I can breathe if I don't have pulmonary circulation? So pulmonary circulation, of course, deals with whatever blood is between your right ventricle and your left atrium. Okay. So whatever is leaving right ventricle, that's going to go through the pulmonic valve into a pulmonary trunk. Pulmonary trunk is going to split into right pulmonary artery and left pulmonary artery. So these are the pulmonary arteries. And that's going to then keep splitting until we get to the lungs, right? And then once we have gotten to the lungs, we will be down to the tiny pulmonary capillaries, right? And the pulmonary capillaries are going to surround alveoli. We'll talk about that again in just a little bit. So that's where the gas exchange is going to take place. And so now that this blood from pulmonic circulation or pulmonary circulation It's coming back, it's now oxygen rich, because as we left the right side of the heart, this was old blood. Right? It was O2 poor, it was CO2 rich. And I'll actually show you numbers in a little bit, right? But as it's coming back into the left side, now it's more oxygenated, right? The CO2 should be lower, and we need to take that back out to systemic circulation. So part of the respiratory system itself involves this, right? Pulmonic circulation. So that's actually tied into the respiratory system, even though it's clearly also part of the cardiovascular system. So sometimes you won't even see a separate chapter that just deals with the respiratory system. Sometimes it gets completely encompassed with the cardiovascular system. And they're like, oh, by the way, you have to have an airway too. So sometimes this doesn't get its own chapter. When I was in school, we never had a separate chapter just for lungs. We talked about, small cell lung cancer, non-small cell lung cancer, and that was pretty much the end of the discussion. Everything else you just kind of read and figured out on your own. And they're like, yeah, just read that chapter, by the way. So again, airway, blood supply. If you ever get asked a trick question about what blood vessels actually supply the lungs themselves, pulmonary vessels don't do it. So trick question. I'm not necessarily going to ask it, but if this ever comes up, if they ever ask what blood vessels supply the lungs themselves, pulmonary vessels won't do it, right? Pulmonary vessels are just for that exchange of CO2 that's in the blood going to the lungs so we can breathe it out, and then O2, which is in the lungs, so we can get it on the blood, right? But that's not supplying any oxygenated blood to the lungs themselves. It has nothing to do with supplying oxygenated blood to the lungs. Every time you supply oxygenated blood to the body, it's got to come from the aorta and a branch from the aorta. So if you ever ask what blood vessels supply the lungs themselves, they're called bronchial arteries. Isn't that a bunch of crap? Just one extra thing to remember, but now you know. So it still follows the rule. If I'm receiving oxygenated blood, you have to get it from a branch off the aorta. And clearly, pulmonary arteries and veins were not branches off the aorta, right? Because the aorta didn't come until you got to the end of the left ventricle. So still following rules. Just one extra detail to remember. But I remember when I was in school, nobody told me these dumb things. So I had to figure them out by missing them on a standardized test or a board exam. And then I'm like, oh, thanks. Would have been nice to know. So here's our airway. Mainly, we start with the trachea, obviously. And the trachea itself made up of C-shaped rings of hyaline cartilage. Eventually, this windpipe is going to split, and we're going to end up forming what's called a bronchial tree, which of course starts with a right and left principal or primary bronchi. So just getting used to terminology. And then these will continue to split and segment, right? And as they segment, we're doing two things. We are decreasing the size of the tube, and we're increasing surface area, right? So as we are using our little airway, again, the trachea itself, it kind of starts as a modified trachea up here when you're in the larynx, right? So larynx, or some people call it a larynx, doesn't really make any difference, right? You can find both spellings acceptable in different places. It's a modified version of the trachea or the windpipe. So of course, with the larynx, you'll have like your thyroid cartilage, your cricoid cartilage. I'll show you a picture of it maybe in a minute, and we can talk about tracheostomy. But this is just a modified portion of the trachea or the windpipe. So once you get into the trachea itself, these are what's called C-shaped rings of hyaline cartilage. And that, again, is unique. So that could be a possible test question in the future, like what part of the body is made up of C-shaped rings of hyaline cartilage? Trachea would be the right answer. And they're C-shaped for a specific reason, because when you're trying to maintain the patent opening, your trachea or your windpipe is always supposed to be open, right? It's slightly flexible. You know, we do have this piece on the back, which could allow for a little bit more of a large opening, but at the same time, it also allows us to swallow food because your esophagus is right behind it, right? And if you've ever seen like a cross section of a trachea and esophagus at the same time, which chances are you probably have not, unless I showed it to you with histology or something like that. Let's say cross section trachea. You'll notice that the esophagus behind it is kind of small right here, right? Like, how are you going to swallow food with that thing? Well, it's okay. This thing will open up as a bolus of food goes through. And then you can already see here how this thing has already been like kind of bent inward. So this is why it's a C-shaped ring of hyaline cartilage, because we can maintain this opening even when we're swallowing food. So imagine that's a closed esophagus behind this, and here's an open esophagus. Right, it's able to bend into that shape. So you can see how that would be useful. Right? So that's a simple test question, even though it's something that we would easily just kind of read and we're like, okay, yeah, got it, fine. You know, sometimes it comes back and it's a question. So as we get into the airway itself, trachea is going to split. Right, so here's our trachea made up of C-shaped rings of hyaline cartilage. And then you'll get to this little structure right here. You'll have something called a carina right there. And this is your first branch, right? Actually, these two are your first branches. So we might call this the right primary branch, or you could call it the right principal branch, because primary, which we just abbreviate that 1 degree sign, means like first, right? But you could also call it principal, which means main, right? So this is the right principal bronchus, it's the right main branch, or it's the first branch going to the right. So right primary bronchus or right principal bronchus. So this is trachea. These are the beginning of the bronchial tree. So you've got the right primary bronchus and the left primary bronchus, also known as right and left principal bronchi. And then on the right side, you have 1, 2, 3 lobar bronchi. On the left side, you have 2 lobar bronchi. So that's important to remember because the right lung has 3 lobes, right? So the right lung has an upper, middle, and lower lobe, or superior, middle, and inferior lobe, and the left lung only has 2 lobes, something like that. Ignore that little piece right there. So it's only got 2, superior and inferior lobe. If you ever swallow a foreign object, the most likely place for a foreign object to go is right lower lobe. Right? So the reason for that is this is just the more direct route. So again, could be a board question based off simple anatomy. If you ever swallow a foreign object, which lobe is it most likely to get stuck in? Right lower lobe, because of the way it's shaped right there. That was another board question I got one time. And again, during normal classes, nobody talks about that crap. So it's always good to learn from your own mistakes, but it's better to learn from somebody else's. So easy peasy. But once somebody explains it to you, you're like, oh, duh, that makes perfect sense. After that, we usually don't memorize lobes. You get into tertiary, quaternary lobes and stuff like that. And at that point, nobody really cares. But again, what's happening is we're trying to increase surface area, and we're trying to decrease basically the size of the tubes, because eventually we need to be down to almost like a single layer width. So we're getting progressively smaller, smaller, smaller until we get down to the alveoli. So sometimes I think it'll be better just to type this in. Let's look at terminal bronchioles, and that should show us the alveoli as well. Eventually you get down to these very, very, very tiny branches that look like this. So these are called, well, this isn't the best picture in the world, but these are called bronchioles, right? And so the bronchioles themselves are really small branches, right? And eventually your terminal bronchioles lead into the clustered sac-like structure called the alveolus, or together we'll call them alveoli. And by the time you're down to the alveolus level and the distal most part of the terminal bronchioles, you're at a single layer of simple squamous epithelium. So again, we've gotten really small by the time we've gotten down here, and it's branched so much to get to that point that we have a really, really large amount of surface area. So usually they'll equate the surface area of the inside of the lungs to about a half a tennis court. So if you were to spread it all out, it would be about the size of a half a tennis court. And while the bronchial tree was branching down, at the same time, your pulmonary vessels were branching down, right? So as your, and this is going to be a very rough drawing, and we'll go back and talk about, where does the trachea branch in just a second. But let's say this is our trachea coming down, and here's our right and left principal bronchi. At the same time that this is happening, let me I'll just get a pencil. At the same time this is happening, my pulmonary trunk is also branching, right? So as these branches of the bronchial tree continue down, they're going to split, right? And the same thing is happening with these pulmonary vessels, right? So eventually they just follow each other, and the pulmonary arteries become eventually arterioles, right? And those eventually become capillaries. So by the time you get down to the tiniest little branches, which of course would just keep going and going, and it's three-dimensional, so it's coming at you as well. So by the time you get down to these little terminal bronchioles with the little tiny alveoli around it, these things have circled around it and turned into capillary beds. So as the bronchial tree is branching, so are the pulmonary vessels. So that's what eventually leads you into this. Okay, and these are branches of pulmonary arteries. These are branches of pulmonary veins. So again, the color is going to get flipped because as I'm leaving, so as I'm leaving the heart, what is the whole role of the right side of the heart? It's to oxygenate the blood. Right, so as we're coming into the right side of the heart, this is venous return. Right, it's old blood. So it's low in O2, high in CO2. Okay, that's what's getting pumped to the lungs. So these would be pulmonary arteries that are carrying blood to the lungs. What state is the blood in at this point? It's deoxygenated blood, right? So that's going to be bluish in color. But as we're coming back in to the left side of the heart, these are pulmonary veins. This is fresh blood, high oxygen that I'm trying to pump out to the body, right? So this would be the reddish in color. So again, don't ever just use color to tell you whether something's an artery or a vein. Arteries and veins will always follow this rule. Arteries will always go away from the heart. Veins will always go toward the heart. That's the better rule to remember, not oxygen versus, deoxygenated. So, but again, now that we're down at this very tiny level, gas exchange can take place. And when gas exchange takes place, it happens through diffusion. Okay, hold on, let me get to it. There we go, diffusion. Diffusion. And that's important. That's important to know. So along the way, our airway is coated by pseudostratified ciliated columnar epithelium, and mixed in with pseudostratified ciliated columnar epithelium, you end up having a lot of things called goblet cells, and goblet cells can make mucus. right? And so the mucus is going to capture any dust or particulate matter. And then on the pseudostratified ciliated columnar epithelium, we're going to have different layers of mucus. One layer is going to be kind of thick and viscous. That's going to capture the dust. Another layer is going to be thin and watery. So it kind of ends up working like this, where you have the thin, watery mucus sitting on top of the alveoli. You have the thick, viscous mucus that capture all the dust sitting on top of that. So the alveoli can wave. That'll move the watery layer of mucus, and then the thick layer of mucus can ride along top of that. And we're constantly cleaning the lungs out that way. So that way we don't just accumulate a bunch of dust and crap in the lungs. The mucus will capture it, and then the ciliated cells will move it out. So pretty much all the way through the tracheo-broncho-alveolar system, most of the way during the branching of these tubes, you're lined with pseudostratified ciliated columnar epithelium all the way until you get to the terminal bronchiole. And then once you get to the very terminal end, like right here, then it switches over to simple squamous epithelium, which will form the alveoli. So a lot of times when you're looking at alveoli, they're just a single layer thick. So gas exchange can take place. And believe it or not, you can actually see little blood vessels in here, like some of these little dark things kind of hidden in between spaces. Those are little capillaries like coming at you. It's easy to see, but who cares? Anywho, so gas exchange will take place and it'll be something like this. Right. So here's your deoxygenated blood coming in, high in CO2, low in O2. So the CO2 is going to diffuse from the blood to the alveolus. The alveolus is going to have high O2, right? So as the blood's going by, CO2 is diffusing from the blood to the alveolus, and then O2 is diffusing from the alveolus into the blood. Now we're heading back toward the left side of the heart. Easy peasy. But let's go back real quick. Let's go back and pick up a couple of things. Branching of the bronchial tree. Sometimes we're not always doing super clinically relevant stuff. I mean, it is, but sometimes we're preparing for boards too. So when your trachea bifurcates and splits into your bronchial tree, the level that this starts is either the T4, T5 disc space. So if we're looking at it from the back, it would be about the same level as the intervertebral disc between the 4th and 5th thoracic vertebra. So the T4, T5 disc space. From the front, this is occurring at the angle of Louis or the sternal angle, right? So if this is your sternum right here, here's your manubrium, your gladius, your xiphoid process. This forms an anatomical landmark that you can palpate on a person, but that little joint that forms right there is called the sternal angle, also known as the angle of Louis, okay? So if we look at that, angle of Louis, T4, T4, you'll see that they're at the same level. So T4, T5, T4, T5 disc space, angle of Louis, boom, same level. That's where your trachea splits. Isn't that fun? Just gives you an idea of where things are underneath. Other things, smoker's cough. Smoker's cough is essentially a change that occurs to our healthy tissues in the airway. And again, most of our airway, all the way down to the alveoli, are lined with pseudostratified ciliated columnar epithelium that has embedded mucus cells, right? And the mucus cells themselves, again, are to capture the dust, but they are naturally swept out. That mucus and the dust is naturally swept out by the cilia, right? And over time, if you smoke a lot, which is going to be the majority of the patients you see with lung problems. The cilia themselves start to become less motile, right? So instead of being all nice and active like this, just constantly sweeping out dust, they're like, hey, get out of here, get out of here, get out of here. They're just kind of like, like that. And some of them die off. And when some of them die off, they end up getting replaced by more mucus cells, right? So you got a little mucus cell that's kicking out mucus here, and you got another mucus cell that's kicking out mucus where you did have cilia before. So this mucus starts to accumulate, right? And I don't have as much cilia to wave it out anymore because a lot of the ciliated cells have died. So the mucus gets stuck in there. So in order to get this accumulated mucus out, you have to cough harder. And when you cough harder, you'll blow air past this, and that'll dislodge the mucus, and it ends up being like this, like that. So you hear them constantly coughing up something, right? They're coughing up something that sounds viscous. So that's a smoker's cough, right? Over time, that's going to inflame the bronchi, the bronchioles, and you get chronic bronchitis. Right? But at the same time, if you have cells that are dying at a fairly rapid rate and they're being replaced by other cells, that itself is called metaplasia. So that itself is bad enough because that's speeding up the process for cancer formation, because metaplasia always precedes what's called anaplasia. And dysplastic cells or anaplastic cells are hallmarks of cancer, right? But metaplasia always comes first, a change of cell type before a loss of cell function. Right. So that's clinically significant. If you ever get asked where does CO2 form, this is supposed to be like a little arrow right there. I don't know why that changed. There we go. So if you ever get asked where does CO2 form in cellular respiration, Krebs cycle is where that happens. Krebs cycle. So this is the Krebs cycle. Also known as the TCA cycle, tricarboxylic acid cycle, or sometimes they just call it the citric acid cycle. The Krebs cycle is where the CO2 forms. So every time a sugar loses a carbon, that's essentially what happens. And when you're going through that Krebs cycle, cell, so this is cellular respiration, right? Cellular respiration. Let's say this is a capillary right here, right? As I'm trying to take oxygen to the cell, again, it's just simple diffusion that takes place. O2 is a fat soluble gas, so it doesn't have to filter or reabsorb. It goes through diffusion, right? And so O2 will move to the interstitial space, and from the interstitial space into the cell. And now you have O2, which is great. Doesn't really have anything to do with glycolysis, but it does allow you to run mitochondrial processes. So that's going to help us here in the mitochondria. And entering into the mitochondria most of the time is some form of sugar. Usually, it doesn't have to be. It can be fat too. But usually it's glucose, which is a 6-carbon sugar, 1, 2, 3, 4, 5, 6 right here. And during glycolysis, we're going to break sugar apart. So that's why it's called glycolysis. We're going to split or break or tear apart sugar, gluco or glycose sugar. So glycolysis or glycolysis is to split apart sugar. So you start off with a 6-carbon glucose molecule. You end it with 2 3-carbon pyruvates. And one of the first things we do when pyruvate moves into the mitochondria is we turn it into a 2-carbon acetyl-CoA, right? So what's going to happen to that other carbon? It's going to become CO2. So every time we take a larger sugar and break it down into a smaller sugar and we're losing a carbon, CO2 forms. So when you take oxaloacetate and combine that with acetyl-CoA, that gives you citrate. 1, 2, 3, 4, 5, 6, which is another 6-carbon sugar. And after a couple of steps, that's going to break down into a 5-carbon sugar and to a 4-carbon sugar, right? So every time we lose a carbon, CO2 forms, CO2 forms. So here's CO2. So 1, 2, 3, CO2. We have 2 pyruvates. So when this next pyruvate enters, that's going to give us 4, 5, 6. So C6H12 O6 plus 6 O2. We need 6 oxygen molecules to do this. So 1, 2, 3, 6, right? And that's going to give us 6 CO2 from both pyruvates plus 6 H2O. That's going to form in the electron transport chain plus energy. So where's the CO2 coming from? All coming from Krebs cycle. It's all coming from Krebs. Easy peasy. Second time around, it's always easier. You know, first time you see this, you're like, shit. Second time around, you're like, oh, okay, yeah, I got it, no problem. So once we form CO2, how do we transport it? If you remember, we will contribute to the acid-base balance. So we're going to buffer that by turning it into bicarbonate ion, which can go back and forth as necessary. But let's review that process again. So during the carbonic acid equilibrium equation, every time we form CO2 and it leaves the cells, so let's say we're forming CO2 in the cells, again, simple diffusion, we'll take it into the blood. So it's going to go out here, it's going to go in here, simple diffusion. Red blood cells have enzymes inside of them that can help convert that CO2 into bicarbonate ion. So we're not going to transport CO2 as CO2 for the most part. I mean, some of it will be, but usually less than 10% is going to stay as CO2 gas. So most of the time we're going to convert CO2 into bicarbonate ion, which is going to be a negative ion. And so chloride that was out there to begin with might shift in while bicarbonate shifts out. Let's not worry about that for right now. But the formation of bicarbonate ion works like this: CO2 plus H2O, water, and the presence of carbonic anhydrase, which the red blood cell has plenty of. That will make H2CO3, which is carbonic acid, right? And the basic definition of an acid is anything that has the ability to donate hydrogen ion to solution. So it's going to deprotonate, give up a hydrogen ion, right? What's left over is what the CO2 is going to be trapped in, which is bicarbonate ion, right? So this is a nice reaction, because if the body ever becomes too acidic, right, then this can just simply capture some of these hydrogen ions and push back in this direction, right? Which is nice, even though it doesn't look that nice because that's called carbonic acid. But as long as it's holding on to the hydrogen and the hydrogen's not floating around freely, then it's not contributing to the acidity. Okay, so it can push back in that direction if we need to. But most of the time, we're going to transport that to the lungs. And then when we get to the lungs, we're just going to reverse this reaction and breathe off the CO2. We're going to breathe off a little bit of the water. Some of the water stays behind, but we'll need to replace some of the water that gets lost. Because when we breathe out, it's moist, right? But yeah, pretty easy reaction. But this reaction itself is an important reaction because it's one of our buffering reactions. Body always pushes toward acid. The more the body does, the more acidic it becomes. So we need ways that we can buffer our solutions, and bicarbonate ends up being a very good buffering molecule. So this is called the carbonic acid equilibrium equation. And it explains why CO2 is also considered an acid, right? Even though CO2 doesn't have a hydrogen to donate, acids typically occur in solution, right? So they're usually aqueous, which is so totally unimportant right now. But water is usually available, is what I'm saying. So this leads to another big idea that I want you to remember, and this will help you in life. This will help you this will be like one of the most useful things you get in life right here. If you forgot everything else that we've talked about so far and you just know this should be adequate, I'm guessing. Here's a head, a face, here's a mouth open, okay? Here's another one. We'll just do this twice. Here's a head, nose, mouth's open, okay? Breathing rate a lot of times is determined by how much CO2 is in the body. So the more CO2 I have, the faster I'll breathe to get it out. But let's just look at when we change our ventilation rate. If we change our ventilation rate, the faster I breathe, the faster I expel CO2. Okay, that's a CO2. It's my halo of light, again, reflecting off the table. The faster we breathe, the more CO2 leaves. The slower we breathe, the more CO2 gets left behind. Okay, so this explains why hyper versus hypoventilation can change pH, right? Because if I hyperventilate, I'm breathing faster, more CO2 is going to leave. And what if CO2 leaves faster than what we can replace it? Then my body is going to increase in pH, or you could say decrease in acidity, right? And become alkaline. If I'm hyperventilating and I'm breathing out CO2 too fast, then I'm losing acid too quickly. So I'm decreasing my acidity, which is the same as saying increasing the pH, which is going to make the body more alkaline. So that could explain respiratory alkalosis. If I breathe too fast. But if I'm breathing too slow, that means I'm not getting CO2 out fast enough, because even at basal metabolic rate, we're producing CO2 in every single cell of the body, right? So we have to breathe at least 7, 8, 9, 10 times a minute just to get that out. Right? Normally it's about 14 breaths per minute. But if I'm breathing too slow, if I'm hypoventilating, then too much CO2 builds up. That's going to decrease my pH, increase my acidity, right? And so we become too acidic. It's an easy concept. So the faster I breathe, the more CO2 that leaves. The slower I breathe, the more CO2 that stays. That will change pH. Why does it change pH? It's based off the carbonic acid equilibrium equation that says CO2 plus H2O yields carbonic acid, yields hydrogen ion. So forget the rest of the equation. Who cares what the rest of the equation says? The more CO2 I have, the more I push this reaction to the right, the more acid I get. Okay. So CO2 and H plus are what's called directly related. CO2 goes up, H plus goes up. If CO2 goes down, H plus goes down. So a lot of times, if I'm trying to rapidly change pH, what can I do? Just breathe faster or slower. So the main organ system that helps us determine pH the fastest is the lungs. But we also have the kidneys, and the kidneys are more thorough because the kidneys can reabsorb or secrete acids and bases, right? So it's more thorough, but it's much slower. And if I have a kidney problem, lungs will come in and help. If I have a lung problem, kidneys will help. But again, that's a good general idea to remember. The faster or slower I breathe determines how much CO2 stays or leaves, right? If I breathe fast, CO2 is leaving faster. If I breathe slow, CO2 is not leaving fast enough, right? So that'll shift our pH. Let's get into some basic numbers here. A lot of times in practice, when you're doing monitoring of a patient, you will read about things called partial pressures. And partial pressure is a derivative of something called Dalton's law, which is pretty straightforward law. Like it basically says total pressure of gases is the sum of the individual gases combined. It's so dumb it doesn't deserve a law. But Dalton coined it, so he gets to take advantage of it. I'm going to come up with a stupid law, and it's going to be called Hayes's principle. But Dalton law just says total pressure of gases is summing up all the little gases together. So they end up being called partial pressures. Like it's contributing to the total. And when you look at PO2 and PCO2, there's certain numbers that we want to hover around. Like PO2, we usually like to say in arterial blood needs to be pretty close to 100, right? And PCO2, usually in arterial blood, we usually like to be on the lower end, like closer to 35. closer to 35. And there's different numbers on here versus here. It's okay. It just came out of slightly different books, but 40, 38, 40, that's fine too. So we'll use 40 since this is the main page here. Let's use 40 and 100. Let's use 40 and 100. So, but again, it's going to be different books, different measurements, different readings, different machines and instruments. So let's use 40. Okay. Let's use this one. So we'll round up 38 to 40, but we'll keep the PO2 at 100. And what this is basically saying, this is all common sense. It looks hard because it's written out in a very long format. But let's pretend this is the old blood right here. And let's go back to our circle diagram. Okay. Let's go back to our circle diagram. And on the circle diagram, let's see. Let me put the circle up top here. Let me put the circle up top. And let's talk about some old blood coming in. Maybe I'll see it myself. So let's get rid of that. I don't like that circle being underneath it. So let's start our circle diagram up here at the heart. Here's old blood coming in. So we'll just put venous return, right? Superior vena cava, inferior vena cava, coronary sinus, repetition, repetition, repetition. Okay. And this is old blood. So old blood means I'm high in CO2. So in this case, let's put that at 45. So let me show you where the number's coming from. So let's say right here, here's the old blood, 45. O2 is going to be low, right? So it's already been spent. So we're going to be down to 40. Okay. So that's where these numbers you can see on the page. So CO2 is going to be elevated, high. O2 is going to be too low, right? So we'll put this at 45. We'll put this at 40. Okay. So that's what's going to be leaving the right side of the heart, going to the lungs. Okay. Once we get to the lungs, this gas exchange can take place. So as the pulmonary vessels continue to branch, right? You have pulmonary arteries, and these arteries eventually become arterioles, and arterioles eventually become capillaries, right? So you end up having these capillaries carrying this deoxygenated high CO2 blood, right? So again, CO2 is going to be high, O2 is going to be relatively low, and that's going to pass by the alveolus. So this is our little alveolus right here. So here's our pulmonary capillary. So this is a pulmonary cap coming from the right side of the heart. So coming from the right side. Here is our alveolus. Let me move it over so it's out of the light. Here's our alveolus. And let's say let's just leave the numbers as is. We'll put it at about 100 for the O2. So the O2 is going to be high. Here, the O2 is very low. We'll put it about 40. Okay. CO2 is high. We're going to put that at 45. And here CO2 is going to be low. Okay. So this CO2 is going to shift out, right? While this O2 shifts in. Okay. So as we're heading back, still in a pulmonary capillary, but now I'm going to turn into venules, which are going to eventually become veins. Now they've exchanged numbers. So now my O2 is high. So let's say partial pressure of O2. So it might just say PO2, 100. The CO2 is now low. It's still got CO2 in there, but just not as much. Right. And this is going to head back to the left side. Right. So coming into the left side is going to be pulmonary veins. This is venous return coming back from the lungs, pulmonary veins. So now we have high O2, low CO2, right? So 140, and that's going to go out to the tissues. So once we get out to the tissues, this is going to become an aorta, and that's going to branch. They're divergent. They're going to get smaller until you eventually get to arterioles. Arterioles eventually become capillaries, right? These capillaries will exchange with a tissue space. So again, we have a high O2 level. So PO2 is going to be 100. So there's going to be a lot of O2, right? PCO2 is going to be relatively small. So PCO2, 40. And then these cells are going to receive this oxygen, right? It's going to diffuse from the capillary to the interstitial space to the cell. The cell will then use these gases plus nutrients it got from the blood as well to metabolize, and CO2 got made as a byproduct. So the O2, as it's shifting out from the blood to the cells, is going to drop, right? The CO2 is going to raise, and then as the blood's leaving the cells, let's say all the tissues of the body, now the O2 is down to 40, and the CO2 is now up to 45, right? So that's where those numbers come from. So it's not complicated. It's not really hard, right? But this, let's say, is venous blood coming back toward the heart. And as we get into the alveoli, we need to flip that around, right? Because we want the O2 or the CO2 to leave, the O2 to come in. So once we pack that blood with fresh oxygen, I want to send this back out to the system. And when we send that back out to the system, the exchange will take place with the body cells, right? So the O2 is going to drop down to 40, CO2 is going to climb back up to 45, and we repeat the process again. Right? So it's not hard. Here's a picture of it right here. So this is venous blood coming in from the right side of the heart. This is pulmonary circulation. This is the high O2 blood going back toward the left side of the heart so it can be pumped out into systemic circulation. We're skipping the heart here. It's going out to systemic circulation. So now the O2 is going to leave the blood, go to the cells. So it's just showing like a muscle cell. Here's a epithelial cell. That's a fat cell. I don't know what that's, a nervous cell, I guess. I don't know. But the O2 is going out so the cells can metabolize, CO2 is coming in. So this was systemic circulation coming from the left side of the heart to the body. Now we're in systemic venous return. So this is what we call VR, right? That's going back to the right side of the heart to start all over again. And then the right side of the heart is going to pump it to the lungs, right? Pick up O2, drop off CO2. This is going to go back to the left side of the heart. Left side of the heart is going to pump out to the body, and we keep repeating the process. It's easy, easy, easy. But one thing that we need to make sure that's happening in the lungs, because again, this is going to tie together a lot of the stuff we've been talking about. One of the things that we said was fundamental to the respiratory system is the respiratory system is made up of two major parts. So again, respiration, you can subdivide into three things: external, internal, cellular. External is like going from the lungs to the blood. Internal is going from the blood to the cells. Cellular is within the cells themselves. And then you just flip that, and the CO2 goes out, the oxygen is going to come back in, all that jazz. But the respiratory system has two main components. You have the airway, which is the tracheo-bronchoalveolar system. And that needs to be patent and open and moving and able to breathe air in and breathe air out. So you got to be able to ventilate with that, but you also have to have pulmonary circulation. And these two have to be able to meet close enough and have a good environment for them to work together, right? So when you get into a picture like this, where you see pulmonary circulation and alveoli meeting up, this gap or this space is a natural space that exists there, has to stay consistent, right? So let me show you what I'm talking about. Anytime you deal with exchange of gases have to occur through membranes, right? O2 and CO2 are both fat-soluble gases. So as I go from, like, say, a cell to the interstitial space, right? So let's say here's the cell and we're going to the interstitial space, and let's say we're picking that up with a capillary. The capillary needs to be pretty close by to pick this up, right? So CO2 is coming out here. It's going to then diffuse, again, going from higher concentration to lower concentration from the interstitial space into the cell, right? The gaps have to maintain some consistency. You don't want a huge gap in between here because gas exchange doesn't take place very well, right? So you don't want a lot of swelling. You don't want a lot of fluid built up in this area. And this is especially problematic when you get into the lungs. So if this is a pulmonary vein, pulmonary, capillary, and pulmonary artery all kind of joined together. So the pulmonary vein will be on this side, pulmonary artery is going to be on this side, capillary is going to be somewhere in the middle. I'm just going to draw it right there. So this was heading from the right side of the heart. This is heading back toward the left side, so we're going in this direction. Here is the alveolus right here. this is where gas exchange has to take place. So again, pulmonary arteries are leaving the right side of the heart going toward the lungs. From the lungs, it's going back toward the left side of the heart. So here we're leaving the right side of the heart going toward the lungs. So that's the deoxygenated blood, right? It's low in O2, but high in CO2. So CO2 needs to leave here, O2 needs to come in here, okay? But at the same time that gas exchange is taking place, you also have, believe it or not, filtration and reabsorption, okay? And the filtration and reabsorption require certain properties, like we have to have proper CHP, you have to have proper ICOP, you have to have proper IHP, you have to have proper CCOP, okay? But guess what would happen? Let me show you something. Guess what would happen? So here's our alveolus again. Here is our pulmonary capillary. I'm just going to draw it kind of straight on that side, just so I'll quit drawing dotted lines. Let's say that our heart itself is failing. We have some type of heart failure. And let's say we have left-sided heart failure, okay? So again, looking forward at the heart, if I have left-sided heart failure, then the problem is with forward flow. I can't get blood out adequately. So we start to get a backup somewhere. So if I have left-sided heart failure, where's the backup going to go? Toward the lungs. So it's going to head this direction, right? Because the backup is heading toward the lungs. That backflow of blood right here is going to cause congestion, right? Like traffic. And that's going to increase my internal pressure inside of here. So pressure on this venous side ends up going up, okay? So let's say everything coming from the right side of the heart is normal. So let's say this is normal. I'm heading out to the lungs, right? We're going to have normal properties, like I'm going to have CHP right here, and that's going to go through filtration. So forget about gas exchange right now, just for a second. Let's forget about gas exchange, but let's just look at normal capillary filtration and reabsorption. So CHP is going to be normal, right? ICOP is going to be normal. Let's assume we have normal contents out here. This is, again, it's just an interstitial space. Oh, I'm sorry. Go ahead. Go ahead.
I don't speak for all men, of course. No one does.
I'm sorry. I might have unmuted you. But if I have proper CHP, right, proper ICOP, and let's say at first we have proper interstitial hydrostatic pressure, eventually that's going to change. Because even if CCOP is normal, even if this is normal, my reabsorption rate is going to diminish, right? So I'll still be getting filtration out here, but my reabsorption rate is going to diminish because even with normal CCOP, I'm having back pressure here. So I can't bring as much fluid in. So what ends up happening is fluid starts to accumulate in this space and IHP starts to go up, right? So that's eventually going to change the shape of this space. So over time, with left-sided heart failure, the gap between your pulmonary capillary, so again, this was coming from the right side of the heart, this is heading back toward the left side of the heart, this was pulmonary arteries, these were pulmonary veins, right? Here's a pulmonary capillary, and we filtered out a lot, but reabsorbed a little because we had back pressure coming back from left-sided heart failure, right? And eventually, because we had more filtration than we had reabsorption, fluid accumulated out in this interstitial space. So that's going to increase the interstitial hydrostatic pressure, right? The fluid pressure in the interstitial space. And not only am I going to start losing my ability to diffuse gases because we've increased this area, so I'm getting less O2 across because it's like getting swept away. So less O2 is coming in, less CO2 is leaving. So some of it gets stuck behind, right? Because some of it's able to cross, some of it's not, because there's too much fluid space. And when you increase the distance that diffusion works, diffusion becomes far less efficient, right? But the IHP is going to start pushing fluid into the alveolus, right? And when that fluid starts to accumulate into the alveolus, we end up getting a cough reflex and we start coughing this fluid out, right? So when we have left-sided heart failure, so if I have left-sided heart failure and I'm having difficulty getting blood out for whatever reason, doesn't matter what the reason is, blood's going to back up into the lungs, and the main sign and symptom I'm going to get is cough and sputum production, right? And this person's going to be tired all the time because the gases themselves aren't saturated in the blood like they should. I can't get rid of the CO2 as well as I should be able to. The kidneys are going to have to start working harder on that. I can't bring in the O2 as well as I used to. So the person's going to be fatigued. They're going to fatigue easily when they're doing activity, and they're going to start coughing and coughing up some type of frothy fluid. Usually it's going to be pink or creamy colored. Right? So that explains the cough and sputum production with left side of heart failure. So isn't that fun? See all the basics that we know, and we can put all those basics together. So, again, why are they getting left-sided heart failure? Could be a multitude of reasons. Could be many things causing that left-sided heart failure, but could be chronic hypertension, and the back pressure here is just too great. The heart tried to compensate for a long period of time, and maybe part of the heart broke. Maybe I broke a valve, and every time it tries to push out a little bit, backs up. So a faulty valve could do it. So a mitral valve prolapse could do it. I could have chronic hypertension and the heart grew to compensate for that, which not only made the valve less efficient, but the heart became less efficient. So that caused blood to back up, because every time you have cardiomegaly, you'll always have congestive heart failure, right? And eventually, when we have this backup of blood going into the lungs, that's going to increase pressure in the lungs, and that's going to give me what's called pulmonary hypertension. Right? And when I have pulmonary hypertension, guess what's going to happen? That's going to back up on the right side. The right side's going to have difficulty pushing against that. And then all of a sudden we start backing up in the whole body, and you get right-sided heart failure as well, because the most common cause of right-sided heart failure is pre-existing left-sided heart failure. Right? But you could have other lung conditions like restrictive lung diseases, which I'll talk about in just a minute, that could also cause right-sided heart failure. Okay? You could have infiltrates in the lungs, like if my alveoli can't open very well, like with sarcoidosis or cystic fibrosis, that can cause a problem and your lungs become more restricting. Or you could have structural changes in the vertebra or the rib cage that can be restricting, so the lungs can't move appropriately. So those sometimes can lead to right-sided heart failure too. Let's take a quick break. Talk about ventilation. Easy stuff we've already talked about before. Tie that into Boyle's law, just in case it comes up on a standardized test. Talk about different types of breathing, air capacities, air volumes, and then pathophys is pretty short. All this right here, pathophys right here, here, and here, I took this directly from that book I was mentioning to you earlier. I don't know if I got a copy with me, but Clinical Pathophysiology Made Ridiculously Simple. It's the best explanation I've ever seen for lung issues. So I just basically copied it word for word for you here. So I'll give them credit for it. But I think I mentioned that to you one of the very first days of class. Clinical Pathophysiology Made Ridiculously Simple by Berkowitz. But let me go ahead and let me scroll back up. We'll take a break. Here's some pictures that I was talking about previously. And we'll take a break till, let's say, 11:20. So I'll be right back. Okay, so we had just got done before our little break there talking about, how does things like congestive heart failure end up affecting the lungs, and we can explain the cough and sputum production now, the fatigue that people are going to be experiencing with left-sided heart failure, and then also the pulmonary hypertension that comes when you get that congestion. That's where the term congestive heart failure comes from, is the lung congestion that comes with it. So that can lead to right-sided heart failure, which eventually is going to lead to the more, visible signs and symptoms of swelling. Usually it'll be their feet first, and their ankles and their hands and their wrists and all that kind of stuff. And they're getting fatigued every time they do some type of activity. And if they have the cough and sputum production along with it, then it's the world's easiest diagnosis. You really don't even need any visual diagnosis to go along with it. You don't need any labs to go with it. You can diagnose it just literally off the exam. So not difficult. When you get into ventilation, of course, is subdivided into inspiration and expiration, or you can call it inhalation and exhalation. And like we mentioned back, it's Oscar clearing his throat. He's got cough and sputum production, or just sputum production. He's a dog. But when we were talking in anatomy 2, we can also subdivide both inspiration and expiration into passive versus forced. So passive, we sometimes also would have referred to it as resting inspiration and expiration. And what determines how quickly we're doing these things and how deeply we're doing these things is, again, usually CO2 levels and pressure. So chemoreceptors, baroreceptors. Let me go down to it. Both pons and medulla are areas of the brain that monitor breathing and they control breathing. So again, the factors that go into it are pressures and chemoception. So the central chemoreceptor is going to be CO2 sensitive, and the higher the CO2 levels are in the body, the more that stimulates the breathing response, right? So if the CO2 levels are pretty high, it usually indicates we're metabolizing faster for the most part. You know, let's just assume everybody's healthy, normal. You know, what's the normal stimulus for breathing? More metabolism. So the more activity I do, the more I metabolize, the more CO2 I produce, the faster I got to get rid of it. So that's why the breathing rate goes up every time you do activity. But there's other reasons CO2 can go up in a person. You know, obviously one of the main things is you have some type of lung problem, right? So if my lungs aren't working well, CO2 can build up even at rest, right? So that's a problem. We can be making more CO2 or more acid in general. So there's plenty of factors that would affect breathing, the ability to breathe, you know, CO2 levels, and O2 levels are important, just not quite as important as CO2. And later we might end up talking about, and I know this would be the ideal place to talk about it, but later we might end up talking about hypercapnia. I think I'll talk about it more in the labs next week. I wanted to keep the respiration and the ventilation as simple as possible, because if we understand the idea and understand that this, you know, has to be maintained at certain levels, certain numbers, we can save some of the pathology a little bit later when we get into lab values, because if I'm going to determine a patient has hypercapnia, that's something I would see on a blood test. So we'll do that next week or 2 weeks from now. But if a patient is hypercapnic or they have hypercapnia, you can't just rely on the CO2 receptor, because it's basically going to be bombarded with high levels of CO2 all the time. And in normal people, normal, healthy individuals, this is what we look for to determine our rate and depth of breathing. It's Oscar again. So it's not O2. But if I'm hypercapnic and CO2 is constantly high, then our normal mechanism starts to fail. It's just like, oh, they're not listening. You know, why are they not breathing the CO2 off? Maybe they can't. Right? Or maybe they're constantly smoking and it's making it too hard to get rid of the CO2, and it's increasing the carbon monoxide and CO2 in the body anyway, right? So then we'd fall back to an O2 level. But this is what comes from what's called the central chemoreceptor. That's going to be the main driving force. You also have peripheral chemoreceptors that can pick up O2, and this would be used again in a patient that's hypercapnic, right? They're just constantly in a state of high CO2. But anywho, most peripheral chemoreceptors that are picking up O2 levels are in some of the major vessels. So places that you'll hear about sometimes that, you know, we pick up peripheral chemoception, like it's picking up O2 levels, is the carotid sinus, which also has quite a few baroreceptors in there, and it's where your carotid arteries kind of split. So again, let's pretend that's a heart, aorta, brachiocephalic trunk, left common carotid, and let's just throw in a left subclavian just for fun. Here's my right common carotid, right subclavian, right? So here's my left common carotid. It's called common because they're conjoined together at this point, and then that'll branch and form internal and external. And when these branches form, you end up getting this enlargement of the carotid artery, and that's called a carotid sinus. And within that carotid sinus, you have chemoreceptors and baroreceptors, right? So if I put too much digital pressure on this part of the artery, that'll actually send feedback to slow the heart down, because it's basically saying, I don't want to over pressurize that blood that's heading to the brain, so we need to slow it down, right? But it also has chemoreceptors in there too. And the chemoreceptors are mostly sensitized to O2 levels, right? So if I'm not getting enough O2 to the brain, that's a problem, right? So it will be sensitized to that, and it can send stimulatory effects to the brain stem, pons and medulla, and then the pons and medulla can send stimulatory effects to the heart and lungs, right? But again, under normal circumstances, normal healthy individuals, what's driving the lungs? Mostly CO2 levels. So as CO2 levels get high, that's going to stimulate the lungs to be more active. What are ways we can make the lungs more active? By changing our rate and depth, right? And depth is usually controlled by how many muscles are involved. So if I'm doing resting or passive inspiration and expiration, it's basically just a diaphragm and then the elastic recoil. So let's talk about that real fast, just in case anybody missed this the first time around. Inspiration or inhalation and expiration or exhalation can both be passive and forced. Passive and forced. And when it's passive, that just means at rest, I don't really have to get a lot involved with it. When it's forced, I'm going to have to use what's called accessory respiratory muscles, right? So it's just in addition to what I'm normally doing, accessory, I'm going to have to engage more muscles to alter the thoracic cavity to a greater degree. So we call them accessory respiratory muscles. Muscles, MN is muscles. Passive inspiration just requires contraction of the diaphragm, right? It's a muscle. It's flat muscle that separates our thoracic and abdominopelvic cavity, and it's stimulated by something called a phrenic nerve. Right? And that is all we need for passive inspiration. Okay? But if I need to breathe in deeper, then that's called forced. So passive, just engaging the diaphragm using the phrenic nerve, and it'll do my normal passive resting inspiration, which will be about a half a liter worth of air, right? But if I need more than that, which will be determined by, again, pressure and chemoreceptors, so baroreceptors and chemoreceptors, mainly CO2, then we can engage more accessory respiratory muscles. So if I need to breathe in deeper, then I can engage muscles around my neck, called scalenes, and muscles around my back, called serratus posterior, superior, and inferior. And this will help to kind of pull the rib cage apart for you. So that the scalenes will help pull the rib cage up toward the neck, and serratus posterior, superior, and serratus posterior, inferior will separate the ribs from each other. So that makes the thoracic cavity much bigger, much faster, right? And if a person has difficulty breathing, you'll sometimes see these things engaged a lot, right? Like if a person's constantly having difficulty breathing, you'll hear it, you'll hear them breathing, right? And you'll see these muscles are sometimes tight around the neck. So that's a good indicator that they're having difficulty because they're having to engage their accessory respiratory muscles more, even at rest. And then the passive expiration is due to elastic recoil. So the relaxation of the diaphragm plus all the connective tissues that just got expanded, they naturally want to go back to their normal shape. So that's elastic recoil. Good reason not to suck on a vacuum hose and then turn it on, reverse, because it can blow out your lungs. You can blow out all that elasticity. That's happened before to people. That's why I bring it up. But it also explains why emphysema won't allow us to get air out anymore, because essentially your internal architecture of your lungs gets destroyed from the inside. And that basically eliminates all your ability to have normal elastic recoil. So I'm having to constantly cough and force stuff out. Forced expiration, abs, and intercostals. Oops. So the muscles in between the ribs. Intercostals are also used for inspiration too, but abs and intercostals are for forced expiration. So when I breathe out, my body goes more like this, squeezing thoracic cavity. When I'm breathing in real deep, my body does more like this. You sit upright, right? So it all makes sense. And then we can engage these as needed, like a little bit or a lot, depending on how deep. So the body's really, really good at doing that where you don't have to think about it, which is nice. That would wear you out. So that's what leads eventually into, I'll come back to this in a minute. Air capacities and air volumes, where at normal passing or passive, resting inspiration and expiration, we're just going through what's called tidal volume, but I can always bring in a lot more if I need to. And when I normally breathe out, it's just tidal volume. Like if I'm just at rest, I breathe in half a liter, I breathe out that same half liter, that's tidal volume. But I can force in 6 times that amount, right? About 3 more liters. And even if I take a normal breath in and breathe that normal breath right back out again, which is that same 500 milliliters, it's just changed composition a little bit, I can still push out another 1 to 1.2 liters. So, right, so that's called inspiratory reserve and expiratory reserve. These are great names for what they are. So it's Oscar again. But tidal volume, again, normal passive breathing, inspiration and expiration would sound something like this. But when you're doing inspiratory reserve, let's do tidal volume in first. Now taking as much air as you can on top of that. So how much did I take in addition to tidal volume? My inspiratory reserve. All right, so it's about another 3 liters. So once you understand these basics, that, throw in a residual volume, the stuff that we can't really touch because our lungs have to stay inflated. You don't want them to collapse. It's hard to open them back up again. All right. Then it's easy to understand these things. So there'll be a question or two on the test that'll just say, here's this number, here's this number, here's this number. Now calculate, say, tidal volume, where you would only need 1 number. Calculate expiratory reserve, or I didn't mean to say expiratory reserve, but calculate expiratory or inspiratory capacity. That's what I'm trying to say. So if let's say, for example, it's easier if I just give you examples. Let's say I give you tidal volume is 0.5 liters, where I could say 500 milliliters, right? And let's say I say inspiratory reserve, expiratory reserve is, I'm just going to make up a number like this. Let's say this is a patient. And I say their inspiratory reserve is 2 liters, right? So they might have some type of restrictive lung disease or something like that. Their expiratory reserve, let's say, is 1 liter. So that really isn't any different than usual. So inspiratory reserve is how much more I can breathe on top, right, of what I was already breathing. So if my tidal volume is half a liter, and then I breathe in as much as I can on top of that, that's my inspiratory reserve, right? Or if I breathe in a half a liter, I breathe out that same half liter, and then I push out as much as I can on top of that. That's another liter, right? In this case, that's expiratory reserve. And now let's say I gave you those and I said, calculate inspiratory volume. Oh, question?
No, sorry.
Oh, no, you're fine. I didn't hear anything. And so inspiratory volume would only need 2 of these numbers, right? I would have to have tidal volume, of course, and inspiratory reserve. All right. So if I say calculate inspiratory volume, I'll give you more than what you need for the calculation, right? And you just plug in. Or I might say, what is vital capacity? So I might end up giving you tidal volume. I might end up giving you inspiratory reserve. I might end up giving you expiratory reserve. I might give you residual volume, and then I'll say calculate vital capacity. right? And so again, if you know what the definition of vital capacity is, let me show you right here. It's inspiratory reserve plus tidal volume plus expiratory volume, right? So I gave you residual on here. You don't need that for this. But if I said, give me total lung volume, then you would need all four. You get it? So if I'm going to ask you questions about these on the test, I'll probably give you more numbers than what you need, and you just plug in what is required. So if I say, give me inspiratory reserve, then all you need is tidal volume, or I keep saying that. I don't mean to keep saying that. If I say, give me inspiratory volume or capacity, then you don't need this number. If I give it to you, you don't need this number if I give it to you. So just leave them out. So if I say tidal volume is 0.5 liter and I say inspiratory reserve is 3 liters, and I ask you what's inspiratory capacity, then just say 3.5. So it's not hard. It's just basically, do you know the definitions of numbers? It's just, it's one of those things that if you know the definitions, it makes your life easier on standardized test again, because that's how they would ask it. They're going to give you more than what you need. You just plug in what's necessary. And then, like when I was in school, they didn't ask me about any of those things, even though I took it all the time to memorize all of it. They just asked me, how do we measure it? They're like, how do we measure air capacities and air volumes? And I'm like, you know, I was like, I don't know what that dumb thing I was blowing on was called. It's just called a spirometer. Right? So. Herring-Brewer reflex, always knows stuff that's got people's names attached to it. Easy standardized test question. Prevents you from overinflating the lungs. So once you reach a certain amount of stretch, you will naturally stop breathing in any further, even though you have the capacity to. You have the stretch, you have the ability, your body will stop you. So you don't overly inflate the lungs. So that's called the Herring-Brewer reflex. Anything that's ever got names on it, always make sure you know it. They always ask those things on standardized tests, always. And then when you get into the pathophysiology, I love the way the clinical pathophysiology, made ridiculously simple, works. It basically says the exact same thing that we said at the very beginning of class. When you are dealing with a healthy respiratory system, you have to have two major components. You have to have an airway, and you have to have the blood that gets to it. But what are things that could change an airway? Well, maybe I'm going to obstruct the amount of stuff that can leave, like the amount of air that can get out, right? So if your airway becomes collapsed or blocked, then you can't get stuff out. Or maybe if I restrict how much air can get in, that's a problem. Or maybe if there's something in the airway other than air, that's a problem. So things like pneumonia, pus, like with cystic fibrosis, or diseases like pneumonia and stuff like that, this can actually form quite a bit, right? Because it's already in an environment that's more prone to that. Plus, it's having difficulty cleaning the airway out all the time. So if you got something in the airway other than air, that's a problem, right? And if you have a problem getting air out that's already in, that's a problem. And if you have a problem getting air in to begin with, that's a problem. So we'll talk about obstructive versus restrictive lung diseases in just a minute. And then blood can be an issue if I can't get blood there. So clots or a pulmonary embolus is an issue. And then if the blood itself has changed its oxygen carrying ability. So if I'm anemic, right? And it's really straightforward, really simple. So again, we'll talk more about anemias when we get into a blood chapter, because these are things that are normally read on labs. We'll talk about more about hypercapnia when we get into a blood chapter, because again, it's something that you would see in a lab, not something that you would necessarily see in an exam, right? But it's really nice the way it's set up. And so when you get into the different types of lung pathologies, that's how it works. So one thing that always comes up that's a little bit confusing for people is, what is the difference between obstructive versus restrictive lung diseases? So I went and color coordinated it for you. The obstructive lung diseases are the ones where you can't get air out, and they're probably the more famous of the lung diseases. So things like chronic bronchitis, emphysema come up the most. But asthma is also an obstructive lung disease. So the problem with chronic bronchitis is you actually have too much mucus, right, or pus that gets in there, and that is indicated by the itis ending, right? So if I have chronic inflammation in the lungs, we start to develop too much fluid in there, and the fluid itself becomes obstructive, right? So rather than being able to get the air out, it gets stuck behind that fluid, that mucus or that pus, and we're constantly coughing to remove it. And that constant cough only irritates the lungs more, right? So it becomes progressive chronic disease, right? So with chronic bronchitis, you're having difficulty getting the air out. So when you try to take new air in, there's nowhere for it to go, right? So it's obstructed from entering because the previous air that was in there couldn't get out, right? So with chronic bronchitis, why can't we get the air out? Because it's obstructed by mucus plugs. When you have emphysema, you get the air in, but you have difficulty getting it out because you've lost your elastic recoil. Because with emphysema, we start to lose some, again, that internal architecture, like scaffolding inside of the alveoli, and they don't have that natural snap back like they should. So as the air tries to get out, right, there's no pushing power, right? So that's emphysema. And then with asthma, your airway itself kind of collapses a little bit, and it's usually due to a lot of what's called eosinophilic granules being released in response to some type of allergen, perhaps. And when those eosinophilic granules get released, the airway essentially shuts down. So again, the air can get in, but the air has difficulty getting back out again. So as you're trying to take new air in, you'll hear that wheezing because you got some air that's still stuck in there trying to get out, new air is trying to get in, but again, the air is trapped. So those are all examples of obstructive lung diseases. So those are some of the most famous of the lung conditions. Those are the COPDs, and all COPDs will be problematic. So chronic bronchitis, emphysema are the two most famous ones. Most people forget asthma belongs to this category because asthma can also be a type of allergy, but it is considered an obstructive lung disease. So obstructive, the problem is getting the air out. Can't get out, right? With restrictive lung diseases, the problem is getting the air in, right? The problem is getting the air in, right? So we can't get the air in. So maybe the lung itself has become too hard, right? And so if my lung itself is supposed to mostly be air pockets, but I got a lot of infiltrates in there, like with sarcoidosis, or if I have a lot of mucus or pus in there with certain types of chronic conditions, like chronic pneumonia, if I have cystic fibrosis and there's stuff inside the lungs that are making the lungs more solid than air, that's a problem. So they'll be restricted in their ability to move. So sarcoidosis. And sarcoidosis can be a differential diagnosis for anything because sarcoidosis can appear in any organ system in the body. A lot of times you'll be able to see it on an x-ray. It'll just be these little dots everywhere. And it'll be solid dots, not hollow dots. Hollow dots we usually think about as tuberculosis. Solid dots we think about as sarcoidosis. And then again, cystic fibrosis. Right, those will make the lungs themselves hard, more restrictive. They don't expand as well. But you could also have problems with the vertebra. So let's pretend that's vertebra, not a trachea. And the ribs that come out from the vertebra, right? And if the vertebra themselves don't move or the ribs themselves don't move very well, that's a problem. So any type of disease where the vertebra get really misshapen or fused together can become a restrictive lung diseases. So there's something called diffuse idiopathic skeletal hyperostosis, where you end up getting a vertebra that's become fused. You could have what's called ankylosing spondylitis, where the vertebra get fused. Is there another one that I wanted to mention to you? Oh, and severe scoliosis. I think I have pictures of all those in the notes. And again, this would actually change the shape of probably one of the lungs. One of the lungs themselves is not going to be able to open and close because the vertebrae are so twisted. So put some of these in the notes for you. The way you can tell somebody has diffuse idiopathic skeletal hyperostosis, they get what's called a dripping candle wax appearance. So here's some of that extra material that has formed on the vertebra that keeps that vertebra from being able to move. It's basically being fused together, right? With ankylosing spondylitis, you end up getting this bamboo spine appearance. So if you look at this part out here, you can just see it's very continuous, and that's not normal. Like when we look at a normal spine, those gaps should be present. You should be able to follow the cortical outline of vertebra. So let's look at, let's look at A to P. That looks pretty normal, right? So here is the cortical outline of the vertebral body right there. Let me just grab this so I can make it bigger. So let me just enlarge this. So here is sacrum. So here's how we know where we are. This is S1. Here is the bottom part of L5 articulating with the sacrum. So here is transverse processes of L5, L4, L3, L2. So L1, T12, we can always figure out where T12 is because that's where the ribs are. So these ribs articulate with the back of the, or on their backside, the rib heads articulate with the vertebra. So if the rib heads for some reason aren't moving very well, or the vertebra themselves aren't moving very well, that's a problem. So with ankylosing spondylitis, what ends up happening is these vertebrae get all fused together and you'll end up seeing them all connected, right? So here we have a clear gap, here there's a clear gap, here there's a clear gap. But when you look at AS or ankylosing spondylitis, look, it's joined together the whole time. So that's what they call a bamboo spine appearance. You also get what's called trolley track sign on here. See those little lines right there going straight up and down? Again, these are just ligaments that have essentially fused. Right. And so you can end up seeing everything connected together. So bamboo spine appearance or trolley track sign appearance. Here's the trolley track again, like railroad track. That's what that means. And it's absent here. So here you can see the diffuse, this is what they mean by diffuse idiopathic skeletal hyperostosis. There's a lot of it, right? So this doesn't look anything like that. This is fused together, this is fused together, but here you can see how the fusion is so widespread. Right? Here it's kind of confined to just the ligaments that are directly attached to the vertebral column. Here you can see some of that really crazy formations that occur with really bad scoliosis. So here's a lung field on this side. Here's the heart right there. On an x-ray, black is air. So here's the lung right here. Here's this lung right here. So that's wild, you know, and here's the heart all on that side. So this person has very little room to breathe. Look at these ribs. They're all ribs. So this person, when they breathe in real deeply, these will all split. These will all kind of do like this. It'll go like that. So they'll probably have a super strong, tight muscles on that one side. Super strong, tight muscles. And those tight muscles will be very tender to the touch too. So if you go and you touch them, they're going to be super sensitive on that side. Let's see. So again, these would all be restrictive lung diseases because the thoracic cavity can't move like normal. Certain changes that we see in people with COPDs, because air gets obstructed inside and you still have to get new air in, one of the changes that you'll end up seeing in those people is they start to get what's called a barrel-shaped chest, right? So with COPDs, the problem is air gets trapped in there and it can't get out. So in order to get enough fresh air in, when the person breathes, they have to overinflate the lungs. And if you do that over and over and over again, essentially what happens is the rib cage gets very thick front to back. So that's called barrel chested. Right? It's called barrel chested. And then you might also notice that they do what's called pursed lip breathing a lot. So if a patient is pretty far along with some of the COPDs, they'll probably have pursed lip breathing. So you'll hear them breathing, and they'll put the lips together because you can exhale better when your lips are like kissy face. So if I breathe in if I breathe in and then I breathe out with my mouth open, you can get out a decent amount of air. But if I push my lips together, you can get out more. It's a weird phenomenon, but it works. So they do that all the time. Helps get the air out. So with some of the COPDs, you'll see barrel chest and pursed lip breathing too. It's just something you can visibly see in the patient. One of the pulmonary function tests, I probably mentioned this to you in anatomy too, but I said, don't worry about it. So now worry about it. It's just a very simple test to distinguish between obstructive versus restrictive lung disease. If you want to do that on a test, again, other than just looking at an x-ray, which will probably tell you a lot of it. You can do what's called the forced expiratory volume in 1 second over what's called forced vital capacity, where you're trying to force the air out, but we're dividing how much air can leave in a short amount of time versus how much air can leave total. Because if you have some type of obstructive lung disease, you're having difficulty getting that air out. You can eventually get it all out, but it's going to take some effort, right? So the FEV1, or the forced expiratory volume in 1 second, is very low, very minimal, because you're obstructed, right? So you can't get that air out quickly. Eventually you can get it all out, right? But it's basically indicating that there's an obstruction somewhere. So that'll help to kind of differentiate obstructive, again, versus restrictive lung diseases, okay? Let's see. So with the restrictive lung diseases, the problem is more or less getting the air in. So the FEV1 is really not going to be changed. This number will be lower. This number will probably be lower just because this number was lower. But the gap between the two won't change. With obstructive, the gap's going to get bigger, so the number is going to be smaller because I can't get the air out fast enough. And then some of the treatments for some of the common diseases, again, we're going to keep it simple for now. Treatment of things like asthma and chronic bronchitis are going to be what you end up seeing a lot of. Obviously, if there's pneumonia, you would give antibiotics. But a lot of times when you're treating these obstructive lung diseases, what we want to do is remove the obstruction, which could be a narrow airway, perhaps, right? So maybe if I can give some type of sympathetic agonist or parasympathetic inhibitor, that will open up the airway. And that's based off this, again, simple idea that when you're doing sympathetic nervous system versus parasympathetic nervous system, one of the changes, so increased heart rate, increased heart contractility, increased respiration rate, right? One of the changes that we see that helps us increase respiration rate is bronchodilation. With parasympathetic, I have bronchoconstriction. So it basically goes back to normal. It's not really getting too small. It's just going back to normal. So if I have something that can stimulate the sympathetic nervous system, which we might call an agonist, right? That's going to increase sympathetic effects, which would increase bronchodilation. So a bronchodilator. Or I could have a parasympathetic blocker or antagonist, which is going to limit bronchoconstriction. So it's going to limit the airway becoming small again, right? So that's why, right, anticholinergics would work, right? Because acetylcholine is the neurotransmitter we use for parasympathetic innervation. And sympathetic agonists work, right? Because we're stimulating sympathetic nervous system or sympathetic effects. And then if you have something that's in the lungs that's causing the obstruction, so let's say I have COPD and it's in the form of chronic bronchitis, again, the inflammation is going to increase the amount of fluid present, right? And that fluid itself, whether it's pus, mucus, whatever, is what's obstructing the air getting out. So if I can decrease the inflammation, I can possibly decrease the fluid as well, the mucus. So treating the inflammation itself is useful for chronic bronchitis. So steroids. Steroids are always pretty easy go-to if you're trying to decrease a lot of inflammation. Right? But we already answered those. And that is all we have for respiratory, at least for now. Again, we'll do some more with respiratory when we get into blood, like different respiratory problems that we can identify on a blood test. But for now, that's it for respiratory system and gas exchange. And that's all the material that we have for lecture exam 2. So going back to last week, week 4 was start of lecture exam 2 material. We did cardiophys. We kind of mostly did cardiopathophysiology here. The Zoom recording for Tuesday of this week, we finished up the last couple of slides from cardiophys, and then we did all of blood flow and pressure. And then today we did respiratory system and gas exchange. Next week, we don't meet on Tuesday. Thursday, we'll do a Zoom Q&A if you have any last minute questions about any of this material. All right. And then our projected due date for lecture exam 2, July 10th. That'll keep you on the best schedule. So next week's kind of nice and open for studying, getting the exam done. And then today, tonight, this weekend, I'll start populating these things, and I'm not going to post it yet. I'm going to wait until toward the end of next week, but I'm going to go ahead and add our last PowerPoints and get some of those Zoom invites going. But for now, just going to leave everything the way you see it as is. If you have any questions, stick around today. If you have any questions next week, feel free to come to our little Zoom Q&A meeting next Thursday. If not, then I probably won't see you again until January 11th. So good luck on your exam if I don't see you. Also, anytime you got questions, email me. You don't have to wait for Zoom Q&As. But let me go ahead and stop the recording here.